going to spend the lecture time and the lab time on the lab. And Thursday we'll do a review for the exam on Tuesday. For, was it chapter 6, I think? Okay, so today we're going to do a lab on calorimetry. And in case I've had a couple of, you're not the only person that's asked me that question. The method that I have copied to use did not have a procedure for determining the calorimeter constant. Remember when I mentioned that when you put your device together and you conduct the experiment, you're going to have everything equal to 0. All the heats are equal to 0. And you can go on up as high as you want. One of these for ours is going to be, it has to be the heat that's attributed to the calorimeter. Remember, we're going to have a device with 2 cups, 2 styrofoam cups and a lid, and it's going to be unique for each group. So we need to know the calorimeter constant that's particular for that group. If you ever do one of these procedures, I'm saying this again so it's on camera. If you ever do one of these procedures again, and it doesn't have a calorimeter constant procedure embedded in the method, then you will make an assumption that the calorimeter constant is equal to 10 joules per degree C. Now, ours is going to be much different than that. It's been my experience. It's going to be different from this. And we're going to determine that calorimeter constant. And to determine the heat, you need to multiply this times something that will cancel the degrees C, the temperature. So that means your change in temperature times the calorimeter constant is its contribution to the total. Okay, so for determining the calorimeter constant, we're going to have 2 other values, heat values here. One is the heat that's due to the hot water, and one that's due to the cold water. Okay, so the formula for this one is going to be a little different. It's going to expand and give you, you're going to have a specific heat value for water times its mass times its change in temperature, and the same thing for this one, only with a different delta T, I'm sure. So this would be for the hot, this will be for the cold. Now, the way that first page is set up, 75 milliliters. So the mass, and we're going to assume that since the density of water is 1 gram per mil, if you've got 75 milliliters, you got 75 grams. So that's why this value is going to be 75 grams for both of them, because one of them is the hot water and one's the cold water. Now, once you have to, well, we're going to need a value for S also, 4.184, I think. That's the value. And the units here are joules per gram degree C. See, if you remember our dimensional analysis, if you go in and say, all right, if this value is supposed to be joules, right, that's a unit of heat or energy, then this term has to reduce itself to joules. So that means you've got to cancel the grams in the denominator, numerator. That's good. This one has to be degrees C to cancel that one, leaves you with joules. So that's one way to check yourself to see if you've got all the factors involved. So we've got to determine a value here for that change in temperature and that change in temperature, and for this change in temperature. And we're going to have values for this and this and this, and there's your unknown right there. So we will solve for that unknown, and that will give us a calorimeter constant that we can use for the rest of the experiments. So if we've got a initial temperature for the hot and initial temperature for the cold, and then we have a final temperature. Why don't I have a final temperature for the hot and cold? Because it's the same value, right? You put the hot and the cold together and they will come to equilibrium. So now the hot and the cold are equal. The hot came down in temperature and the cold went up in temperature. So let's say, that's just for argument's sake, let's say this is 90 degrees. And say the cold is, I don't know, 40 degrees. That's a little warm, but this is hypothetical. Where are they going to meet? Well, we'd expect them to meet somewhere in the middle because of the same mass. Right? So we would expect that to be maybe 65. Okay. So when they come to equilibrium, that one drops to 65 and this one goes up to 65. So the values here would be final minus initial. So for the hot, the final is 65 minus 90. And here is 65 final minus 40. Okay. All right, so that means this one's going to be a negative value at 25 degrees. So this would be 25, a negative 25 degrees C. And this will be a positive 25 degrees C. Okay. Now, how about the calorimeter? What temperature did it start at? Remember the procedure? The cold water goes in the calorimeter first. So it starts off at the same temperature as the cold. So its initial temperature is 40. Its final temperature is 65. Right? Because everything comes to equilibrium. All same temperature. So it's going to be the same as this one. This will be 25 degrees C. So now we have all our values here, 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 there, there. Oops, I forgot this one. 4.184. And this is our unknown. So with those values, if we reduce this to, let's see, let me get my calculator out. This is just hypothetical, but it will give us a number. If this is 25, then we have 25C here. That's all that's left from this one. This one is minus 25 times 75 times 4.184. And this is minus 7845. Minus 7845 joules. And the third one, see, we don't need this one now because we've only got 3. And the third one is going to be 4.184. I think that's right. And 75 times that, and then 25 times that, which is 7845. I didn't plan it that way. It just worked out. So these are equal. They cancel. Positive, negative. That means 25C, 0 equals 25C, and C equals 1 over 25. That's a pretty small C. Oh, I know what happened. I created these values without even considering that. I need to use different values. Otherwise, the calorimeter constant is going to be worthless. Let's make this one, say, 25. That's closer to room temperature, isn't it? Yep. Okay, so Now we're going to do 25. Excuse me. Same here, 65. Final minus initial. This one, though, is going to be 65 minus 25. Okay. So that's 40. And this is going to be the same thing. So that's 40. Now let's go back, and this is going to be 40C. Nope. Wait a minute. Oh. That's an unknown. I shouldn't have left that 10 in there. So this is 40 times C. This is 4.184, 75, and 25. I've already done this one, haven't I? 78, 40. So this one's okay. This one's going to be different. So this one's 40. 75 times and 4.184. This one is 12,552. Okay. Now if I add these together, already in my calculator, so I do this. And this says that 40C here, and if this is a positive value, I'm going to bring it on this side to be negative, is going to be 4707. And then C would be 40 divided into that. It's a pretty big number. 118 joules per degree C. Okay, this is just an illustration. Yours hopefully will be a lot smaller than that. Now, the fact that this is negative simply means that the calorimeter gave up energy in the process. But the constant itself is the absolute value, because when you do the calculation, the constant its sign is generated by that value. So it would just be 118, even though it comes out calculated negative. The absolute value is the true value for your calorimeter constant. So that's the first step. We got to get that calorimeter constant, and we just use room temperature distilled water, and I've got water in there boiling now. I just need the temperatures of each. And a very important tip is that when you're going to add two things together in your calorimeter, you want to measure the temperature immediately before you combine them. If you measure them measure the temperature of the hot water while it's boiling, and then you pour it out and measure it, and then you pour it in, it's not that temperature anymore. Okay. So that's your calorimeter constant. All right. Oh, there's an example.
Is mix the same as final?
Yes. Yes. Oh, and there's the specific heat of water. Okay. Okay, this one doesn't have it. Now the Brightspace copy of the method included pre-lab questions, but the one I handed out in class didn't. And that's the one that I'm going to work off of. But these pre-lab questions are useful. So I'm going to talk about those. Yeah, we got time. So since I don't have them on the board, I'm going to have to write them up here. So this pre-lab question 1 is 1 mole of acid and 1 mole of base react to form 1 mole of water. So that would be, a generic would be acid and base. This is aqueous, aqueous. And you'll learn in the second semester that one of the products of an acid-base reaction is the cation and the anion come together. And it could be, I'm going to call them aqueous, doesn't have to be. They could precipitate. Plus hydrogen and OH. That always makes water. So 1 mole of this, 1 mole of that makes 1 mole of that. That's the stoichiometric ratio of the two. Okay. So in your method, you remember, I hope you remember, that we had, let's see. Acid is, well, actually, that wouldn't work for her. Okay. All right, let me use what we actually, it's going into the method. I should have done that first. The acid is sulfuric. And the base is sodium hydroxide. That'd probably make more sense. Okay, so we need 2 of these, and that makes 2 of those. So if the molar ratio is actually a half a mole of this is required to neutralize a mole of that. 1 mole of this and 2 moles of that. So the question is kind of worded wrong. Well, no, it's proposing 1 mole of acid, 1 mole of base, make 1 mole of water. All right, so 1 mole of, or 2 moles of base, this part of the molecule, 2 of those, and 2 of these makes 2 of those. All right, so the ratio is still 1 to 1 to 1. Did I lose anybody? Okay. So if we're going to use half molar sodium sulfuric acid and 1 molar base, does that work out? Right. If we were to use, say, 50 milliliters of this and 50 milliliters of this, would that work out to, let's see, this would be 50 millimoles, right, of sodium hydroxide, or 100 millimoles of OH, right? Because we have, well, no, that's not right. It's 50 millimoles because it's 1 to 1. But this one is 25 millimoles of H2SO4, which means 50 millimoles of H plus, right? Because for each millimole of this, we got 2 hydrogens. But for each millimole of this, we only got 1 hydroxyl. Okay. Blank stares. So this is the stoichiometric ratio of hydrogens to oxygens to make 50 millimoles of water. 1, 1, 1. That's what that first statement means. Okay. What are the chances that you're going to be able to measure the volume of acid and the volume of base so accurately that you're going to get a stoichiometric mixture? 0. You will not do it. You'll either have too much base or too much acid. Well, we want to establish a complete reaction. So we make one of them excess, right? Which one do we want to run out? Well, we want this one to run out in this case. So we make this one excess. Right? So if this is going to be limiting, we make this one excess. That means in the method, we're going to use 60 milliliters, which means 30 millimoles or 60 millimoles of hydrogen. That means this is the one that determines the outcome over here. So we are going to end up with 50 millimoles of water, and we're going to have some excess acid left over. Okay. So when we're calculating the concentration, well, actually, let's save that for later. The answer to the question is an excess of one substance means that the neutralization will go to completion. Otherwise, we don't know which one's which. We want to be able to say which one, we want to be able to determine actually how much water is produced. And this is one way to do it. Determine a limiting factor. This is the limiting one. This is excess. So we base our calculations on that one. Just like always. Okay. I got number 2 coming up. You're an engineer assigned to choose a material that will protect a spaceship from destructive heat when it re-enters the atmosphere. It's called an ablative heat shield. That's the way they used to make them, and they've gone back to making them that way in some cases. They use a heat shield that absorbs the energy of re-entry, the friction from re-entry. And as it heats up to the point where it is turns into a liquid, it sloughs off, takes the heat with it. But if we're designing the heat shield to protect the capsule, and our 2 choices are aluminum or iron, and aluminum, the specific heat for aluminum is 24.35 joules per gram degree C. Oops. Oh, sorry. It's molar heat capacity. Mole degree C. And we have, for iron, we have 25.10 joules per mole degree C. And this is extremely hypothetical, because when you're blasting a capsule into space, weight's an issue, right? So we're saying they're already in space, and we can swap out the heat shields in space. We just do a spacewalk and put a different one on. The question is, based upon this information only, which one would be a better heat shield? Look at what it's saying. We want the temperature to change less as it absorbs heat. So if they absorb the same amount of heat, then, or actually, which one would absorb more heat for a single degree change in temperature? Iron. See, iron would absorb more of the heat for a degree change. So iron would be a better heat shield in this hypothetical case. Now they still use ceramic tiles. Ceramic tiles are excellent heat shield because they have a low heat capacity. So the argument is different for ceramic tiles, because what they do is they don't transfer the heat through to the body of the spacecraft. In fact, they heat up so high on the surface that they heat up the air, and the air sloughs off. So the tile stays intact, hopefully. And the heat is carried away by ionized air. So it's a different proposition altogether. The difference between ceramic heat shields and ablative heat shields. Okay, the last one I have here is the enthalpy of solution of sodium hydroxide is minus 44.5 kilojoules per mole. Okay, enthalpy of solution. So we're going to mark this as enthalpy of solution for sodium hydroxide is equal to minus 44.5 kilojoules per mole. We're also given 10 grams of sodium hydroxide. So if we say the mass of sodium hydroxide for our experiments is 10 grams, and it's dissolved in 75 milliliters of water. So the actually the mass of water or the volume of water, actually, I've got to be specific. The volume of water is 75 mils. We'll make the conversion later if we need to. Oops. 75 milliliters of water. So we put that in the water. And the water's temperature, the initial temperature of the water is 21.1 degrees Celsius. What would be the maximum temperature attained? The heat capacity of the calorimeter is 10 joules per degree C. All right, so we're going to use 10 joules per degree C as the calorimeter constant. All right, so the question again is, what would be the maximum temperature attained, the final temperature? So we would set it up like this. Right? Everything that happens in that calorimeter is equal to 0. There's a heat capacity for the calorimeter. There's a heat capacity for the water, and there's a heat attributed to solution. Okay. That heat would be this. But this is per mole. So we're going to have to, in order to do that value right there, we've got to find out what the actual heat is from 10 grams of, let's see, go back to the question. Yeah, maximum temperature. So the heat that's due to the dissolution of sodium hydroxide, yeah, we need to know how many moles this is. Let's see. That's the calorimeter. That's the water. This is, yes. So how many moles is 10 grams of sodium hydroxide? Right, conversion factor, grams to moles. So what's the molar mass of sodium hydroxide? Let's see. Round it off, 23.00 for the sodium, oxygen 16, and hydrogen is 1.01. So that's 1, 0, 40, 40.01. So if we divide 40.01 into 10, we get 0.2499. 0.249. 0.99 moles. Okay. Now we're given the molar heat capacity of sodium hydroxide. So we know what this term is going to be right here. This is 0.2499 moles times this value, minus 44.5. Actually, times 10 to the third joules per mole, right? Because that's kilo. And we got apples and apples, not apples and oranges. So we have to change that to joules. I just changed the kilo to 1,000, right? Stuck it on there. All right, so that's this term. How about this term? This term is going to be 4.184, which is S, and then 75 grams of water. And then final temperature minus initial temperature, which is 21.1 degrees C. Okay, and that's kind of scrunched in there. How about the heat for the calorimeter? Well, the calorimeter only has two terms in it. The calorimeter constant, which is 10 joules per degree C, and then that is awful bunched up, isn't it? Let me spread it out some. Put it over here. Joules per degree C times final temperature minus the initial temperature. So, it's going to be the same temperature as the water, 21.1 degrees C. So there are our three terms. Anybody any questions about how we got there? Calorimeter constant. And this is our unknown. We're looking for that value right there. All right, so let's reduce it some. All right, let's see. 0 is going to be equal to 10 times TF minus 10 times minus 21.1. So it's minus 211 joules. That's this first term. 10 times 21.1 is 211. This one is going to be 4.184 times 75, then times 21.1, or actually 313.8 times final temperature minus, and then 21.1 is 6621. 6621. So this is that term, and that term gives you this term. And this one is from that term times this unknown. Okay? And the last term will give us a bona fide number, 2449, and 44.5 exponent 3 times is minus 1089.8. 1, 2, 3. Nope. And 4. This is no 8, 9, 10. Okay. And moles cancel, so this is joules. Okay, so far so good. All right. So let's combine. Let's combine our final temperature terms. These two. All right, so 10 plus 313.8 is 323.8 TF. Then we've got a minus 211. and a minus 6621 and a minus 10898. Yep. So this is minus 17730. That look right? Yep. Okay. So if we want to put positives on one side and positive and change, we'll move this one over here, make it a positive. So 323.8 TF equals 17730, and TF is that value divided by 323.8, which is 54.8. Let's see. Close enough. I'm a little off than the one I worked in my key because I used that value right there. In the key, I used 40. And then this one, so that gives me 0.25. And that threw it off just a little bit. Questions? Okay. So those are all the pre-lab questions that you'll find in the Brightspace document. And before long, I'm going to go in and change that just to remove that. Or actually, what I may do is leave it there. And then next semester, I'll hand out a different with the pre-labs in it. Because I think it's helpful to run through these calculations. All right. So, and I've also got, let's see, we're going to have a neutralization acid base. Talked about that one. We're going to dissolve sodium carbonate in water and see which way the temperature goes, up or down. And then sodium bicarbonate, see which way the temperature goes, up or down. And we're going to actually calculate the heats of solution for sodium carbonate and sodium bicarbonate. And then you would compare them with this table at the very end, right here. So these values are in kilojoules per mole. And we're not going to do sodium chloride. That just happened to be part of that table I extracted from a document. We're going to be looking at sodium carbonate, sodium bicarbonate, and H plus OH yields water. That's our neutralization. And the units of measure are kilojoules per mole. Now, kilojoules per mole are easy to understand for sodium carbonate and sodium bicarbonate because you just need to calculate the moles of each one of those depending on the mass that you dissolve in the solution. Right? But how about kilojoules per mole of a neutralization? It's based upon kilojoules per mole of water produced. And if we know, well, I've erased it. If we know the limiting reactant is sodium hydroxide, and it's a one-to-one relationship, if you know the moles of sodium hydroxide, you know the moles of water. So whatever heat value you get from that reaction, you divide by the number of moles of water that were produced. I think I've got sample calculations in there. We'll look at them in just a minute. This is a case of trying to see the forest for the trees. There's lots of math involved. You can get bogged down in the math. But what you need to do is back up and see what the experiment is actually doing. And I always go back to this equation. Right. That encapsulates everything that's happening in that calorimeter. The heat of this term plus the heat of that term plus the heat of that term all have to be 0. Then you break it down into particulars. How do you get this heat? Well, it's the calorimeter. Then it's just the calorimeter constant times the change in temperature. If it's something with a specific heat, it's SM delta T. If it's a heat of solution, then you're going to get a whole heat term in joules. Then you do something with it. Okay, so we would get, say, joules of heat released by the dissolution of sodium carbonate or sodium bicarbonate in water. It would be that heat. It'd be simply joules. That's it. Then you would do something with it. You would prorate it by the number of moles of sodium carbonate or sodium bicarbonate, or prorate it based upon the number of moles of water produced. Okay. So it all goes back to that equation. Let's see. Is there any more down here? Yeah, sample calculations. So this one is a sample calculation for sodium hydrogen carbonate, which is sodium bicarbonate. Those are sample terms. You don't use those terms for your report. You'll have terms of your own to put in there. And notice that the unknown for this reaction is Q of the reaction. That's what we identify as the heat term for the reaction itself. Then once you get that value in joules here, then you prorate it based upon the moles of the compound or the salt that you're dissolving. And that's the value that you compare to the table. So if this one is 16.8 kilojoules per mole for sodium bicarbonate, 8 kilojoules per mole sodium carbonate, it's about one kilojoule off per mole. And of course, you'd want to do a percent error. Let's see. This is an example for acid-base reaction. Okay. So you need to calculate the number of moles of water produced. And we do that based upon the moles of sodium hydroxide because it's the limiting reactant. So 50 grams of sodium hydroxide right here is part of the calorimeter reaction. But when you prorate it by the amount of water, you need to determine how much water was actually produced. And in this case, actually, it'll be the same for your reaction because you're using 50 milliliters of 1 molar. So that's 50 millimolar, which would be 0.05 moles. And you divide that into the heat term that you get from your calculation. Q of reaction. There it is again. Okay. All right, we've got some post-lab questions. And this is a case where the laboratory questions are going to be part of your calculations anyway. So when you get to those questions in your report, just reference where you actually did the calculation. Unless it says, oh, in this case, why or why not. Then you have to elaborate. Let's see. These right here, for some reason, they tend to give students trouble. Commercial hot and cold packs are based upon chemical and physical changes. The first one says design your own hot pack using sodium carbonate. All right, so that gives the plot away. Right, sodium carbonate should get warmer. Sodium bicarbonate should get colder. Design your own hot pack using sodium carbonate. If the desired temperature of the hot pack is 50 degrees, how many grams of sodium carbonate must be dissolved in a pack that contains 500 milliliters of water at room temperature? Assume that all the heat is transferred to the water. All right, let me set this one up. We're not going to calculate, but let me set it up. So here we are again. This is Q of the reaction. Q of the water. Right? The heat change in the water, the Q of the reaction, and does it say ignore the calorimetry? It doesn't say, so we have to ignore the calorimeter. Right? So we really only have two terms. What's the heat produced by the reaction, and what's the heat absorbed by the water? Okay, so for the heat absorbed by the water, we need a final temperature and an initial temperature. Right. So the temperature initial and temperature final are given. Right. The water starting off at 20 degrees. And it's ending at 50 degrees, correct? All right. So this second term over here is going to be 4.184 joules per gram degree C times what's the mass of the water? 500 milliliters is 500 grams. Right? And then the change in temperature is going to be, final temperature is 50 minus 20. Okay, so every term is filled for this one, for the water. Okay, for this one, we want to know what heat is evolved here. And okay, that's the unknown. Right? So if you calculate this value, it looks like it's going to come out a positive value, right? But when we move it to this side, it's a negative value, which confirms that the reaction is exothermic. Okay? That will tell you how much heat is produced by this reaction. It's going to give you a Q value. And what else we need is the ultimate question is how many grams of sodium carbonate? So we need the mass of sodium carbonate dissolved in 500 milliliters. All right, if we have the Q for that reaction, what else do we need? We don't have the information in the problem. We have to go look it up. So that's where that table comes in. Sodium carbonate, minus 23.3 kilojoules per mole. So the delta H for that reaction is minus 23.3 kilojoules per mole. Okay. So if this is the amount of heat per mole, we can find out how many moles of sodium carbonate we need. Because this is going to tell us how much heat. This is going to tell us the joules. We just have to convert it to kilojoules and use this as a conversion factor. All right. If you guys tell me what that value is, then I'll finish working it. Okay. And we use a similar method to the next question. You got a value for that?
Yeah.
Okay.
That's 62760.
760.
Yep, even.
And that's joules. Okay. Plus Q reaction. Well, 0. So the heat of the reaction, and this is an extensive property because it depends on how much we use. It's not intensive. This is intensive, but the overall is extensive property. So this is minus 62,760 joules, which is minus 62.76 kilojoules. Okay. So how do we find out how many moles? Well, we want the number of moles on top, right? Kilojoules on the top, bottom. So minus 23.3 kilojoules per mole. Divide that into 62.76, and that tells you how many moles of sodium carbonate you need. Got a value?
Yeah, that's what I got is 2.6935.
Moles of sodium carbonate. All right, we're getting somewhere. Now, if we want to know mass, you guys know how to do that. 2.6935 moles. What we need is a conversion factor, moles to grams. So what's the molar mass of sodium carbonate? Well, let's see, 2 sodiums is 2346, right? Carbon is 12.01, and 3 times 16 is click, 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 48. Okay. So we need, let's see, this is going to be 1, 0, 16, and 1 and 9 is 10. 106.01. Right? Yeah.
I got 285.538.
Okay, so now's the time to round off. Let's round it off to that. Grams of sodium carbonate in 500 milliliters of water. That's a lot, but it will produce that change in temperature. 285.5 grams of sodium carbonate in 500 milliliters of water will produce a temperature change of 20 to 50 degrees when it gets hot. Now, this seems difficult. The only answer I've got for that is you haven't worked enough of them. You'll follow a similar procedure for this for the other question, which is a cold pack using sodium bicarbonate. What was it? Oops, skipped it. Went too far. Here we go. No, that's not it. Below it. Yeah. There it is. So we want to go from 20 degrees down to 1 degree. Right? So set yourself up a table so you know initial and final temperatures. Otherwise, if you put them into this calculation wrong, you'll get the wrong answer. And then you'll calculate how much sodium bicarbonate. You'll need a different molar mass, obviously, but the steps are the same. Let's see. Oh, and it gives you a sort of a, yeah, it sort of walks you through it part way. Let's see. So that's 4 and 5. Oh, and these will be different for each group. 1, 2, and 3. Any questions? How about the procedure itself? Questions about the procedure? About safety concern? Boiling water for one. Hot plate and boiling water. Glassware, broken glassware. Thermometer. Well, these thermometers are not mercury based, so they're just glassware problems. That's about it. You're not going to be snorting any sodium carbonate or sodium bicarbonate, so you don't have to worry about that.
Sulfuric acid.
Sulfuric acid, yep. It's corrosive. Sodium hydroxide at that concentration is also corrosive. I think it's anything less than pH 2 or greater than pH 11 is considered corrosive by the OSHA. Okay.